So our next speaker is also from Western, also a biologist, but a different kind of biologist. An ecologist.
An ecologist.
Definitely an ecologist. Her name is Andrea Boyer, and she's going to be talking to us about the effects of recurring inclement weather cues on the stress response and feeding behavior of white-throated sparrows.
So that title is a big title. Had I changed this title, this is the title of my thesis, just to how is climate change impacting avian species, I may not have scared so many non-scientists away, but we'll move on. So ecology, why is an ecologist here? Why do we care about climate change? So ecologists look at how organisms interact with other species, with their own species. So we're looking at both abiotic factors and biotic factors. But with respect to abiotic factors, there was a really great paper published last year by Sutherland et al. That identified 100 fundamental questions in ecology. So these questions highlight the complex set of challenges that ecologists are faced with today. So there were several hundred ecologists surveyed across the world in many different fields in ecology, and they came up with this list of 100 fundamental questions. So one of the subcategories of questions is human impacts and global change. So we're seeing now that a fundamental question in ecology is definitely with respect to global change. So one of the questions was, what determines the rate at which species distributions respond to climate change? So where are they moving, and what determines the rate of the shifts that they're making? Another great question from this paper was, in the face of rapid environmental change, what is determining whether species are adapting, shifting their range, or going extinct? But the question that really interested me was, how do natural communities respond to increased frequency of extreme weather events predicted under global change? And in particular, with respect to me, I wanted to look at how avian communities respond to this. So climate change, although we saw many definitions this morning, or this afternoon rather, for the climate change is basically fluctuations in temperature and precipitation. I'm also talking about the increased frequency of inclement weather, the increase of extreme weather events that we're seeing, and also more unpredictable events that we're seeing. And as a result, climate change is affecting many natural systems and populations across the globe. So avian responses to climate change, what are we actually seeing already as a result of climate change in the avian world? So we're seeing delays or advancements in their life history stages. And this is dealing with both breeding, so when birds are deciding to lay their eggs, and also migration, so spring and summer, spring and autumn migration, delays or advancements with respect to changing temperature. We're also seeing a decreased lifetime reproductive success rates. So climate change and changes in their environment are creating unfavorable breeding conditions. So it's becoming harder for these birds to breed, and as a result, it's creating low nestling survival. And that feeds into the third point, that there's just a limited food supply when temperatures are changing. So it becomes difficult for nestling survival. We're also seeing range shifts, so both northward and also altitudinal. This is an example here of the American goldfinch, what their range was and what their range is expected to become, and is already on the way to looking like that for sure. So with northward range shifts, they can keep going up to a certain point, but the real problem lies with altitudinal range shifts. There's several species now that as temperatures are increasing, they're going up and up the mountain, but eventually they're going to reach that summit, and then they will ultimately be faced with extinction. So right now, about half of North America's birds are now under threat as a result of climate change. And about 1/3 of all the North American birds will lose over 50% of their current range, again, directly related to changes in temperature and precipitation, and many of which will not survive. So this leads us to saying that we are now also seeing extirpations, so local extinctions, and also extinctions of individual species. So basically species have two options now. They can either adapt to this change, they can shift what they're doing, or they're going to be faced with extinction. So going back to this inclement weather, for the purpose of my talk, inclement weather is typically associated with low pressure systems. And along with these low pressure systems, we're seeing changes in temperature, significant precipitation, an increase in wind, and also decreasing barometric pressure, which, as you can expect, is posing several threats to small birds. So the challenges that are created by this inclement weather, in particular to birds, regulating their body temperature. So being able to adapt to extreme temperatures is becoming a problem. Like I mentioned before, locating food sources. So with an increase in precipitation, particularly for ground-feeding species, if the ground is always covered in snow, it's creating an additional problem for finding food. Successful migration, which I talked about before. So this graph here is not actually precipitation radar. This is actually migration radar. And as we know, that's a significant line of storms across the U.S. So that's creating problems. Maintaining territory, so territorial birds that need to maintain their territory, they're being forced to move out because of this increase in storms. And ultimately, it's causing a problem with survival. So how are birds actually surviving winter and surviving these storms? So birds can actually increase their cold resistance throughout the winter months, and they do so by lowering their metabolic rates and also increasing their fat and energy reserves. So birds create what is known as emergency fat reserves, which when they sense that a storm is coming, they can access food while it's there and put on fat that they can pull from at a later date. They also seek shelter amongst dense foliage and cavities. They huddle together to keep warm, just like we would. The primary means of regulating thermogenesis among birds is shivering, and they do this by moving their flight muscles back and forth, and ultimately fleeing the area, but this isn't always an option. So we have meteorologists that can predict inclement weather for us. But can species predict this weather? We actually know now that birds can actually detect when the temperature is decreasing or increasing, and they can also detect changes in barometric pressure. So the detection of barometric pressure is actually known across several taxa now, but in particular I'm going to focus on birds, where we know that as a result of changing pressure, they are altering their behavior and physiology. So going back to one of these fundamental questions in ecology, this really helped shape the question for my master's thesis, which was how do recurrent winter weather cues affect physiology and behavior in a songbird species? So looking at these recurrent weather cues, I wanted to look at, with respect to physiology, the stress levels. So how are stress levels changing with increased inclement weather? And also body composition. So how is fat mass, lean mass, or overall mass changing? And also feeding behavior. And I looked at this by simulating inclement storms approaching, residing, and subsiding in the area. So predictions for my study were with an increased level, increased frequency of storms. I'm expecting to see an increased level in baseline stress levels. Also an increase in fat stores, so this goes back to these emergency fat reserves that I talked about. And also an increased feeding duration as the pressure is decreasing. So how am I going to simulate these weather cues? So here at Western, at the Advanced Facility for Avian Research, we have a hypobaric climatic wind tunnel. So what this wind tunnel actually allows us to do is simulate pressure conditions up to 7 kilometers in altitude, which is about 37 kilopascals, which is very low pressure, obviously. There's also a temperature control between minus 15 and 30 degrees Celsius. And there's also a level of recreating wind conditions. So these conditions combined allow us to simulate pressure systems passing through. So my study species were white-throated sparrows. They're a migrating species. They're a good species for my project, particularly because they do experience storms in both their winter and spring habitats, so they already experience these storms naturally. My experimental design, I of course had my control and my experimental group held at identical conditions. They were held at a fixed temperature of 11 degrees Celsius, which is an average wintertime high for their wintering grounds, held at ambient pressure, so whatever was being experienced in London at that time, and a fixed amount of food. So my experimental group, I moved them into the wind tunnel once a week for a 24-hour period where they experienced an environmental manipulation, which I will get to further. And then after this 24-hour period, they return back to their environmental chambers. So the actual environmental manipulation to simulate this low pressure system passing through, what did I do? I dropped temperature from 11 degrees down to 1 degree Celsius, in addition to decreasing barometric pressure from ambient down to 96.1 kilopascals. And these two variables are realistic, again, for their wintering grounds. So here's just kind of an overview of what my birds went through. The black line here is the ambient pressure experienced in London, so what all my control birds experienced. And then these dips in pressure that you can see in the red lines were my simulated low pressure systems. And just to remind you, with these decreases in pressure, we also saw that decrease in temperature. So I should also mention my control group moved into the wind tunnel once a week just to eliminate any differences in stress with respect to changing environments. So my data collection, looking at stress levels were taken from blood, which I collected every other week. And for body composition, I ran quantitative magnetic resonance scans. For those of you not familiar, this is just a non-invasive way to easily obtain body composition, so fat mass, lean mass, which were also completed every other week. My feeding behavior analysis was taken using video tracking software, so we can see here, this is just the setup of my cages, and the video tracking software in red just tracks the bird's movement over time. And it also knows where the food cups are, so they can tell me how long was spent actually feeding. So moving on to my results. Baseline stress levels did significantly decrease over time, however, not between groups, there was no effect. So the manipulations did not act as a chronic stressor to increase the baseline levels. However, I do still expect that it was an acute source of stress, but I, of course, wasn't looking for that. Looking at fat mass, my experimental birds did have a significantly higher amount of fat mass compared to my control birds. So this tells me that the manipulations did elicit enough of a response to change body composition, and that goes back again to the emergency fat reserves that I was talking about earlier. There was a significant increase in the feeding duration over time. So concluding remarks, as a result of these environmental manipulations, I saw no change in stress levels, a change in body composition, so I saw an increase in fat mass, and in addition, this graph wasn't shown, but I saw an increase in lean mass as well. And I also saw the increased feeding duration across weeks. So what does this mean? So an increase of just one additional low pressure system per week was enough to elicit a response. So it did change body composition, but it didn't affect baseline levels of stress, but again, it likely did act as an acute stressor. We also know that we have a lot more to learn and a lot more studies that can be conducted. So overall, my study was the first long-term manipulation study in a controlled setting. So this is basically the building block of manipulation studies because really none have been done before this. It further provides us with evidence that birds are detecting changes in their environment and they are responding accordingly. And it's the hopes that this project and hopefully more to come will gain insight into how birds are responding to this increase in inclement weather. So thank you very much, and we'll take questions.
We have exactly 10 minutes for questions.
Okay.
Amazing. Questions?
No one's sticking their hands up, I have lots of needless questions to ask. So if it's not eating more, why do they put on more body mass when you essentially give them more cold stress when you'd expect metabolic rate to be higher?
So there's two answers to that question. The first being the feeding that is showing up on there is just in this 24-hour period. So it's not showing what's happening the day before or the day after, or as they're seeing this increased frequency, how they're responding. But also too, they probably know that, oh, this storm is coming. That tells them that they need to put on these fat stores, whereas birds not experiencing a storm just kind of eat and don't feel the need to hang on to it.
And also you just have feeding rate, right? You don't actually have how much they consumed.
No,
So
so
they could have just been eating more in the same amount of time.
So that was a visual observation, but it's very difficult to measure because they're kind of jumping around in food cups and there's food going everywhere. So I couldn't take the weight of the food that was actually ingested. However, there was a visual observation that my experimental birds, the food cups were empty after this 24-hour period, whereas control birds, there was still however much left over. So I should also add that it was a predetermined amount of food in that 24 hours. So it was just enough that they can kind of survive off of.
So, so we're seeing that. So the birds who were subjected to these simulated severe weather things were putting on fat, which is kind of good because that's what they need to do to survive inclement weather. Because what we really want to know is, you know, how inclement weather is going to affect the survival rate in the wild. Do we have any information about that, or? Are they?
Sorry, I don't really understand your question.
So, you know, this kind of looks like it's good news, right? Because, you know, subject them to inclement weather and they put on weight, and that'll help them survive they put on fat, and that'll help them survive the inclement weather.
Right. So there's only a certain extent to which they can keep doing this. Like I said, just an increase in one storm system per week elicited this change in body composition, but the main focus of what I wanted to look at is the stress. So how is stress changing? I expect that the increased amount of storms that I'm going to simulate per week is going to cause an increase in stress. So the fact that we're just seeing them put fat on now, that is a good thing. But I presume that it's definitely affecting stress levels. So for my next study, I will be simulating more storms in addition to trying to find a way to take stress levels actually after that 24-hour period, so not looking at baseline levels, and that's where the problems will occur if stress levels continue to increase.
So there was another hand here.
Not really. I might have to rethink it. I think this is not in the case of birds. You wouldn't call this phenomenon plasticity, right?
So there is a level of plasticity, phenotypic plasticity that they're experiencing, but it's so with respect to changing their body composition. But with respect to changing stress levels and how they're responding to that, so that's going to become entering the realm of adaptive evolution. So that's where we're seeing these changes, which are starting to cause problems when you're changes in the timing of life history stages. So all that kind of combined is where the problems are coming out of.
And in that case, I think also that like this increased body fat and lean mass. This is in one population that you don't run into these crazy insect problems where one population or one species within actually have this great variability. So that would be actually could be used as a control group and as a climate indicator too when we take it the other way around.
Yeah.
Sorry.
That is fascinating.
I need to interject. Why yes? I mean, why is it not the case that, well look, this is the first study that's been done like this. Other birds are going to be completely different. I mean, they might all just die, or they might
so
deal with it in a very different
it's
way.
definitely a species-based approach, but I mean, this is the very first study. However, I mean, it's been done. There's been short-term studies done on other songbird species, and they also saw the same thing. They see an increase in fat, but this is short-term studies. So just with the studies that we have now, we are seeing that the changes in body composition are occurring across species. There's just not much evidence to go off of.
But they're
right
all
now.
really small, right?
The birds.
The birds that
Yeah. So they're just songbird species.
You can,
Sorry, there's a...
I was going to answer your question. You do see between populations, you can sometimes see some changes, some differences in the same species in terms of like how big they might be. So you find some northern species might be slightly bigger, which means they can hold more body heat than some other southern species. So it allows them to tolerate a little bit more or a little bit, you know, bigger changes in temperature and other environmental changes, but it's not anywhere near to the extent that insects show plasticity. Like, it's not really comparable. So hopefully that helps answer it. Sorry.
Eric?
So you were expecting to see some kind of, or hoping to see some kind of change in stress. I assume you were taking blood samples on the control as well?
Yes.
Okay. Could that be a reason why not seeing stress? I mean, that's a pretty big stress. If you take blood sample on control and on your birds that you put in conditions that perhaps they are like evolutionary, they've met those conditions, they're used to, I don't know. Have you considered that as an explanation for not seeing stress difference between your group, your two groups?
When you're taking avian blood samples, you have a 3-minute period where stress levels aren't going to change. So they are experiencing the same amount of stress with respect to being in a cage and being inside, being put into the wind tunnel. But you have a 3-minute period before corticosterone levels actually start to increase as a result of handling stress. So all blood samples are taken within that 3-minute period. So handling stress isn't a factor yet. Yeah.
2 more minutes if anyone has another question.
Right. So I'm just wondering about the frequency, because effectively you've just got a slight increase in the frequency of these events may clearly happen anyway. Is there any way you could design this experiment, either do it off-season so they're not already adapted to it? Because it may be that all you're seeing is that you've got a baseline change in their biology that is, like I was talking about with the sort of the baseline plasticity trade-offs, that maybe you just they don't have an opportunity to have any more plasticity. Maybe they're already stressed out of their brains because they get 8, pressure events over the course of the winter, and 12 makes no more difference. So is there a way that you could do it in a different time of year, or at a time that would give them that would sort of make it a different stress?
Yeah, so I chose to do winter storms in particular with these species because they are experiencing more storms in their wintering grounds, but like you said, if it was in the summer and you see an increase in storms there, perhaps low pressure systems and increasing the temperature. But like I said, this is just a very first experiment, so it'll certainly be something to think about for further studies to come. But an increased frequency in storms the entire year. So it's hard to plan a study like this, especially because London is experiencing X amount of storms. It's just not really something that I can...
I wonder if your response variable isn't measuring the right kind of thing. I wonder if what you should do is chuck them at -20 and see how long it takes them. This is what I do with our insects. Chuck them at -20 and see how long it takes them to starve to death. You know, and actually, you know, this is why I don't work on vertebrates. You know, and basically get a measure of like performance, right? Because it may be that you're only going to see this playing out when they're, you know, because this is only the cue that the storm is going to come. -1 is not much of a winter storm. And instead, they need to have no access to food, and so you need to compare the groups that way. I'm not suggesting this is what you should do.
No. So those variables are picked based on, so they're wintering over in the southern United States. So
right. Okay.
So that is a pretty severe temperature for down there.
Great. Well, let's thank our speaker.
Thank you.